Okay, this is the follow-up to my last video that defined what a reference angle was and how to find them. Here we're actually going to what do we do with some of these reference angles, at least the beginnings to it. It allows us to know some trig values outside of the acute angles between 0 and pi over 2 radians, those first quadrant acute angles, and right equivalent statements that be useful substitutions. As we start getting into more complicated trig equations, we start solving, we want to do some rewriting, some substitutions, so on and so forth. So we are going to now use reference angles in conjunction with our circular definition. So sine of theta equals y over r, cosine of theta equals x over r, and tangent of theta equals y over x. For example, find the exact values of sine, cosine, and tangent for the given angle. So I have this angle theta, and this angle 5 pi over 6 is a second quadrant angle. It's a little less than 1 pi. That's the angle 5 pi over 6-ish. My reference angle will be this distance here. Using what we did before to calculate that out, I didn't quite make it a full half a revolution. We didn't make it quite half a revolution. I'm a little shy of it. How shy of it am I? 1 pi over 6 radians. So as I work with this, although my question is about 5 pi over 6, I'm going to use a reference angle of pi over 6 to calculate these values. All right, so let's start with the sine function. So I want to know what is the sine value of 5 pi over 6. Well, if I look at my diagram again, I would want to choose some point on the terminal ray with some x and y coordinate, and then some radius r. Well, the pi over 6 angle that we calculated, if I draw that on a separate coordinate plane, and I look at the initial ray, and I look at the terminal ray, and I choose a point x, y with some radius r. What I want to see, and I hope that we could see, is that the point xy on my 5 pi over 6 diagram and the xy on my pi over 6 diagram are reflections of each other across the y-axis. So in this particular case, the two x coordinates, that x coordinate and that x coordinate, are going to have opposite values. The two y coordinates are actually going to have the same exact value. Since this angle is pi over 6 and this angle is pi over 6, we could use the similar triangle, congruent triangle argument to say that all those values are going to be the same. So if I calculate, if I calculate sine of pi over 6, and this is something from our common values, sine of pi over 6 is going to be 1/2. That's just something we know from our chart. Then I know, well, when I go to sine of 5 pi over 6, I'm going to have the same radius of 2 and the same y coordinate of 1. So actually sine of 5 pi over 6 also equals 1/2. Sine function defined as y over r. For pi over 6, y is 1, r is 2. Because of the reflection over the y-axis to 5 pi over 6, up here, we get the same values. So that's how we could calculate sine of 5 pi over 6, by using a reference angle and knowledge of our common values. Let me clean this up a little bit. And we'll do the same thing for cosine. Now, cosine of 5 pi over 6, we want to know that value. But what we're going to do is we're going to use the cosine value of pi over 6 to help us out. In this particular case, cosine of pi over 6 we know to be root 3 over 2. And the cosine function is defined as x over r. And because of the reflection, we said here these two x coordinates are going to be opposite of each other. So as I find cosine of 5 pi over 6, I'm not going to have root 3, but I'm going to have negative root 3, which does make sense because 5 pi over 6 is a second quadrant angle. In the second quadrant, x coordinates are negative, so that does make sense. Over my radius of 2, now the radius stays the same. A radius is just always a positive absolute value. So cosine of 5 pi over 6 is negative root 3 over 2. So if we put together, to be successful with these tasks, you need to be able to do the following. You need to be able to find a reference angle. You need to know and be able to use your, I'm going to call them here the x, y, r. I'm going to call them the x, y, r definitions of your trig. That's your circular definitions. And you need to know that your common trig values, you need to be able to use them and apply them appropriately. And then you're watching the signs, you're watching the quadrants to make sure everything stays the same. And once again, I guess we need to use reflections. So we're kind of talking about the transformations that we were talking about before and how the x and y coordinates relate to each other. All right? So that's one example. And I think we'll do another example in this video before we move on as well. Here we've got another case where we're going to find an exact value. Just a point of emphasis, I guess, here. Anytime you see that you're going to be asked for an exact value, you know it's going to have to do with something with your 30-degree angles, 45-degree angles, 60-degree angles, or it's going to be quadrantial, meaning the terminal ray is on an axis. Because you don't know anything else. And we actually just don't even worry about anything else. Everything else is a calculator exercise. So we've got to find the exact value of sine, cosine, and tangent for theta equals 315 degrees. The last example was in radians. This one is going to be in degrees. So I need to start by finding my reference angle for 315 degrees. Draw a quick coordinate plane. Standard position, initial ray, terminal ray, third quadrant angle. This value right here is going to be the reference angle. You might want to pause the video, take a moment, figure out that reference angle yourself, and come back. Okay, to find the reference angle, I would say that I've almost completed one full revolution, being 360 degrees, but I haven't quite. I've covered 315 of the 360 degrees. So if I subtract, I'll find out the amount that I didn't cover, and I get 45 degrees. So my reference angle is going to be 45 degrees. I'm going to use that 45-degree angle. I'm going to use my knowledge of my common values of the trig functions. I'm going to use some reflection stuff to put together the values of this. So I'm going to draw a second coordinate plane, and I'm going to draw my 45-degree angle. And so I can make a comparison again. Now what I'll see is if on the 315 degree, if I choose some x, y with a radius, and then I take that and I reflect it over the y-axis, sorry, if I reflect it over the x-axis, so I'm now in the first quadrant, and I have my x, my y, and my r, I would be able to say that these two x's are both going to have the same value. And I would say that these two y's are going to have opposite values. I guess furthermore, I could say that the r's are going to be the same. And that's what it's all about. What is the same? What is the different? What is different? And the things that are different are going to be different because they're just opposites, nothing more than that. So if I want to find sine of 315 degrees, I would start by working with sine of 45 degrees. Sine of 45 degrees we know is root 2 over 2. And don't forget that that is defined as a y over an r. According to my diagram, my y's, we talked about those as I reflect from the 315 degree terminal ray to the 45 degree terminal ray. My y's are going to be opposites. So I change my root 2 to a negative root 2. And we talked about as I go from my 315 degree terminal ray to my 45 degree terminal ray, that my radii stay the same, is 2. So sine of 315 degrees is negative root 2 over 2. Cosine of 315 degrees equals, well, I'm going to use cosine of 45 degrees to help me out. Cosine of 45 degrees is also root 2 over 2, being defined as x over r. We talked about when I reflect, the x's are actually going to stay the same. So that's going to stay the same as root 2. My radii stay the same, and that's going to be 2. So cosine of 315 degrees is root 2 over 2. And then finally, tangent of 45 degrees is equal to 1. I might want to write that as 1 over 1 to remember that it's y over x. Let me go over here. So tangent of 315 degrees. As I reflect my y's, they're opposites. So that in the first quadrant, we know it's 1, so I'm going to make it negative 1 over my x-coordinate, which stays the same as 1, which simplifies to a negative 1. So tangent of 315 degrees is negative 1. All right, so there's a couple of examples about how we use reference angles, our circular definitions, using the signs, SIGNS, of some values to find exact values of some trig functions. I hope you found it helpful. Keep practicing, and good work.